Electrochemistry and batteries. Electrochemistry brings together the study of two separate domains, electricity and chemical reactions. The same electrons which are so critical to chemical reactions are also responsible for the flow of electricity in electric circuits. The first electric generator worked by using a machine to create static electricity. By rubbing dissimilar materials together, it was not connected to chemistry at all. So for hundreds of years, chemistry and electricity were studied separately. The connection between them first emerged due to experiments by Galvani in 1791. He noticed that a frog's muscle would twitch when touched by two metals. He wrote that this was a special biological electricity. Volta and others later proposed that this was the same electricity that had been observed earlier, but was generated by two dissimilar metals being in contact with the fluid in the frog. Those dissimilar materials in an electrolyte generated electricity, which made the muscle twitch. Volta in 1800 proved that dissimilar metals in an electrolyte would generate electricity, and he built the first electrochemical battery. It used zinc and copper plates, two dissimilar metals, separated by cloth soaked in brine, which is just salt water, and that was the electrolyte. That's the blue thing here. And here, not sure if this was one of Volta's or somebody else, but that's what it looks like. Here's the modern version of Volta's design. The copper top is used to market this type of battery. Below shows how the zinc and copper are now rolled together with electrolyte in between. And they're calling it a jelly roll here. So you have a negative electrode collector down at the bottom, a metal bottom cover, metal top cover, safety valve, insulation ring, and a positive electrode connector. And the roll here is the two metals separated by the electrolyte. The positive terminal of a battery is called its cathode. The negative terminal is its anode. Electrons naturally flow from the negative terminal to the positive terminal, from the anode to the cathode. By connecting electrical devices between these two terminals, here's an electrical device, the battery can power them. Now, physics problems are solved using conventional electric current. It's the flow of positive charges from the positive terminal to the negative terminal. It was defined by Ben Franklin before the electron and its charge was discovered. But what's really happening is our electrons are moving, and that's what we're going to use in this unit. Current is the flow of electrons. The theoretical electric potential difference between the anode and cathode is called the battery's electromotive force, or EMF. The EMF is what drives electrons through a circuit. The greater the EMF, the greater the force exerted on each electron. It is also called the cell potential and is designated E sub cell. It is measured in volts. The volt is a measure of the difference in electric potential energy per unit charge at two different locations, in this case between the anode and cathode. 1 volt is the electric potential required to impart 1 joule of energy to a charge of 1 coulomb. A coulomb is very, very large, by the way. In a voltaic cell, EMF is equal to E cell. In a spontaneous reaction, E cell is positive. EMF depends on the cell reaction involved. We'll be working with standard conditions here, which is 1 molar, 1 atmosphere, and 25 degrees Celsius. So again, under standard conditions, E cell is called E0 cell. E0 cell is the standard cell potential. The development and improvement of batteries is on the cutting edge of improving sustainable human life on Earth. New improved batteries make possible watches, laptops, tablets, and phones, storage for energy created by wind and solar power, energy for hybrid and electric cars, energy for drones and other mobile devices, and many more innovations. There is ongoing research on improving batteries from the very small to the very large for all these purposes and more. Improving batteries will be a major field of study for this foreseeable future. The efficiency of batteries is critically important. When a battery is used, it generates heat, which is not useful for doing work. The efficiency of a battery is the percentage of its electric potential energy which does work. It doesn't generate heat. The more efficient the battery is, the more work it can do and the less heat it generates. We now depend on batteries being rechargeable. Whether it's the battery in our car, which gets recharged by the alternator when driven, or that of our phones, laptops, or tablets, which we charge at night, or the storage battery used during the day to store energy from solar cells for use at night. The capacity to be recharged depends on the electrochemical reactions in a battery being reversible in an efficient manner. Efforts are underway to make recharging faster and more efficient. Why not have electric car and phone batteries that could recharge in a few minutes rather than hours? For many applications, the amount of energy which can be stored in a battery of the smallest size and mass is critical. This is the energy density of a battery. If the energy density of batteries in electric cars could be doubled or tripled, their range would be as well, making them very much more competitive with gasoline-powered cars. If we could travel 1,000 kilometers on a single charge and recharging only took minutes, electric cars would be much more competitive. This all comes down to improving battery technology, which is all about electrochemistry. Electrochemistry, though, goes way beyond batteries. It also explains how we can electrolyze water to store energy until we get it back by burning the hydrogen back into water or powering fuel cells. To prevent corrosion, which is rusting of cars, ships, and any exposed metal, plate materials with a metal surface. But we'll begin our study of electrochemistry with batteries, where it all began.